For decades, the spacecraft silently traversed the solar system's outskirts, steadily transmitting data that received little fanfare until now. NASA is now reeling from a startling realization. Didn't merely drift into deep space. It stumbled upon something truly extraordinary at the edge of our solar system. This wasn't just the boundary we expected. It was a sharp, mysterious threshold marked by sudden spikes in radiation and unexpected shifts in plasma behavior. The discovery calls into question much of what scientists thought they understood about the solar system's outermost limits. A mission that far outlived its purpose. 2 was launched in 1977 with a planned lifespan of just 5 years, 10 if luck held out. Yet against staggering odds, it has continued its mission for nearly 50 years, battling intense radiation, deep space cold, and the void between planets. The probe has remained active, sending whispers of information across the void of space. Following its twin, 2 became one of the only human-made objects to enter interstellar space. This transition was not merely symbolic. It was confirmed by abrupt measurable changes in the environment surrounding the craft. The spacecraft's instruments recorded sudden shifts in particle density and radiation levels, signaling its passage through the heliopause, the outer boundary of the Sun's influence. Instead of a slow fade from solar control, 2 passed through what seemed like an invisible curtain separating 2 distinct cosmic domains. Contrary to older assumptions of a gradual decrease in solar influence, the transition was instant and dramatic, suggesting our solar system is wrapped in a more defined bubble than previously imagined. Just outside this protective shell, conditions intensified. Radiation levels spiked and particle behavior changed sharply. Without proper shielding, any craft entering this zone would face a barrage of harsh galactic conditions. Findings didn't just confirm the heliopause's existence. They changed how we see it. What was once believed to be a fading edge now appears to act like a cosmic barrier, shielding our solar system from more dangerous galactic elements. The fact that the solar magnetic field was closely aligned with the galactic magnetic field outside was particularly surprising, defying earlier theories that predicted a chaotic mismatched interface. A sharp transition into the unknown. When 2 crossed this outer limit, scientists were astonished by how fast the environmental conditions changed. Instead of a gradual shift, the data showed abrupt jumps in plasma concentration and radiation intensity, akin to stepping from a calm room into a turbulent storm. The boundary, known as the heliopause, had once been thought to be broad and blurry. In truth, it turned out to be much more precise and sudden than expected. Outside this zone, high-energy cosmic rays increased dramatically by about 70%. This provided firm evidence that the heliosphere acts as a kind of energetic filter, dampening harmful cosmic rays before they penetrate inward. Once beyond it, 2 was suddenly exposed to a harsher galactic climate full of fast-moving, highly energetic particles. Additionally, 2's data suggested that the heliosphere may not be spherical at all. The Sun's movement through space along with fluctuations from solar cycles could distort this boundary into more of a teardrop or irregular shape. 1 crossed into interstellar space at around 119 astronomical units, while 2 made the transition at approximately 121 astronomical units, a small but telling difference that supports the idea of a shifting and uneven frontier. This boundary appears to breathe, expanding and contracting over time, possibly due to the Sun's 11-year activity cycle. Temperature spikes, fluctuations in magnetic field direction, and jumps in particle density all hint that this edge of the solar system is a dynamic, changeable zone, not a static limit. As it continued beyond the heliopause, 2 began to experience what scientists call interstellar weather. Unpredictable changes in radiation and magnetic fields likely caused by distant galactic phenomena such as stellar winds or ancient supernovae. While it doesn't carry the equipment to observe these events directly, its subtle readings offer indirect clues about the broader conditions in interstellar space. Why the heliosphere is crucial. The Sun constantly emits a stream of charged particles, the solar wind, which travels outward and shapes a vast region around our solar system called the heliosphere. This region, along with the Sun's magnetic field, provides a kind of buffer zone, shielding planets and spacecraft from much of the high-energy radiation found elsewhere in the galaxy. For decades, scientists debated where exactly the influence of the Sun fades and the galactic environment takes over. 2 settled the debate by showing that this handover happened suddenly and over a surprisingly narrow range. The heliosphere, once thought to taper off slowly, instead ends in a well-defined frontier. Monitoring changes in plasma behavior, magnetic field alignment, and particle speed, 2 helped scientists pinpoint where the solar wind crashes into the interstellar medium. Inside this region, the Sun is in charge. Outside, the rules change. New theories have since emerged suggesting that the heliosphere may have a tail like a comet dragged behind the Sun as it moves through the galaxy. The front of the heliosphere might be compressed while the rear could stretch out in a long wake. Evidence from both spacecraft supports the view of an asymmetrical dynamic boundary constantly influenced by internal solar activity and external galactic forces. Even small changes in solar output like a solar flare or coronal mass ejection could temporarily distort the shape or location of the heliopause. In the same way, interstellar shocks or radiation storms might push back from the outside. These findings have major implications for future space missions, especially those that venture beyond the Sun's protective bubble. Spacecraft and astronauts would need advanced shielding to survive in regions where galactic radiation runs free. A magnetic surprise. One of the most unexpected revelations from TOS data was the near alignment of the Sun's magnetic field with the interstellar magnetic field just beyond the heliopause. Scientists had expected some degree of misalignment, turbulence even. But what they found was a smooth handoff between the 2 fields. This opens up new questions about the nature of the space surrounding our solar system. Could it be that the local interstellar environment has been shaped by the Sun's long-term outflows? Or did we simply emerge into a patch of the galaxy that aligns unusually well with our own magnetic structure? This alignment also affects the way cosmic rays move. These charged particles follow magnetic field lines. So, if the fields are aligned, it could allow for easier penetration of galactic radiation into the solar system, something scientists will need to consider as they plan future interstellar missions. While one had only limited functionality in its plasma instruments at the time of crossing, TOS's more complete sensor suite provided stronger evidence of these magnetic characteristics. This lends greater weight to the notion that the heliopause is far less chaotic than previously assumed. Complicating matters is the Sun's magnetic cycle, which flips polarity every 11 years. These shifts can stretch or compress the heliosphere, meaning that the magnetic conditions encountered may have been linked to solar activity at the time. Still, the smooth alignment remains a puzzle that challenges conventional models of how solar and galactic environments interact. Comparing 1 and 2's crossings. Although both 1 and 2 eventually broke into interstellar space,